Hi all, welcome to Module 6. We'll be talking about databases and getting a basic introduction to what databases are. Our main objective in this module is to understand the need for a database and why a web app would even need a database. Once we understand that, we'll look at popular DBMS systems and what problems a DBMS or a database management system is supposed to solve. And then we look at what the architecture looks like if we have a web server and a DBMS. So to understand a database, the first thing to understand is when we need to handle data specifically. To understand databases, it's first very important to understand the use cases of when we need to actually handle data and what we even mean by data in the context of a web application. Broadly and non-technically, whenever we serve or save content is typically when we need to handle data. Let's look at a few examples. Whenever you see pages that have a common structure but different content on the page, for example, product pages on an e-commerce site or the article pages that we created last week. Another example is if you go to Facebook or Flickr.com or YouTube and you see a lot of content that is served to users, video content or PDF content or images. Another example would be when you're using an e-commerce site and you're saving your delivery address, or when you're logging into a site and saving username and password. That's another place where user-generated content needs to be handled explicitly. Users might also generate content of different types, for example, images or audio files. And this also needs to be handled explicitly. It is important to understand that we need to separate code and data. We need to separate the part of our application that sort of runs the application and is the logic of the application, and the part of the application that handles the data. And let's look at a few examples to make this separation of code and data more clear. So let's look at a Flipkart. And if you look at the Flipkart homepage, which is an e-commerce site, this top bit of the Flipkart site, which is the bit in the red rectangular box, this part is what I would say is generated using the code bit of the Flipkart web app, right? Because these kind of things are sort of hard-coded or necessarily a part of the Flipkart website. But if you look at this portion, which is in the green box, this part is definitely data, because this is the part of the web app that will change very frequently and that has very different characteristics in the way it is managed or in the way it is used on the web app from this part of the content. For example, if you look at the banner called Deals of the Day, this portion of the web app that displays this section that shows this heading called Deals of the Day is a part of the code. The content of what this banner contains is what I would say is a part of the data of the website. If you look at Gmail, and this is a screenshot of my inbox, the bits of the app that are responsible for generating this menu structure on the side, that are responsible for structuring this inbox into three sections, say important and unread, important and unread. These sections are a part of the code of the web app. And the email content, which is content that changes quite frequently, that depends on other people sending me emails, this is a part of the data of the Gmail web app. In this portion, if you look at the word inbox or start or sent mail, these are the code portions of the web app, and this is the data portion of the web app. As a last example, let's look at Facebook. Almost everything on Facebook is the data portion of the web app, apart from the structure of the overall site. Let's look at this section here, which is very definite and which does not change. But this bit inside the green box, which is a post, this is definitely the data portion of the application. So what is our current understanding of how we handle data? And let's build upon the examples that we used last week where we templated article content. So we had 3 articles and we were displaying 3 articles in the same way with the same structure on article pages. We looked at the example of incrementing a counter, an API that increases a counter every time you hit the API, and an API that takes as an input a name and outputs a list of names that have been submitted so far to the web app. These were the 3 places in our application where we were handling data, and let's see how we handled them so far. So this is what our source code looked like for the web app. We had an articles object. This is a JavaScript data structure, and this data structure contains the article content. So this is where our data was stored. If we look at the counter example where the initial value of the counter was 0, and then every time the /counter URL was called, the counter was incremented, we were handling our data, which is just one integer, as a variable inside our source code, right? And similarly, when we had the names endpoint, where if you contact the /submit name endpoint and a name was given to the URL endpoint, it was being stored in an array. So the data portion of the application was kind of inside a variable called names, which was an array, right? This was okay for a very, very simple example, but there are fairly big problems with doing things this way. For example, the article data, which was a part of our source code, what if we had 10,000 articles? What if we had a few GB or a few 100 GB worth of articles? Would we store that inside this data structure inside our source code? Would we have a few million lines inside our source code which just handle data? In fact, apart from the fact that this does not seem natural, we can't even have that much as a part of our program source code, because every time the program is loaded, that much amount of RAM would be consumed to load the program. And if the data was a few 100 GB, then it is not even possible for a program source code to load. The other kind of problem that one can have is that even if one does not have a few thousand articles, for any web app, the way you maintain code and the way you maintain data are two very separate activities. Just to take a very simple example, developers maintain the source code, but people who maintain the data for example, a blog site might not be developers. They might be people who manage content, and the life cycles and the tools that you use to manipulate code and manipulate data in this case would be very different. The third problem that we have in our way of doing things, in our very simple way of doing things that we've used so far, is that the counter and the names array, which was a data structure that was modified as the app was used, this data was not persisted. That means every time the web server restarted, that information was lost. So every time we restarted a web server, our counter started from 0. Every time we restarted a web server, our names array started off as an empty array. So if we ever have a restart, or if our server crashes, or we need to take it down for maintenance, or we update code, we would lose all the information that we've gotten so far. So these were the problems. This is the problem in doing things by storing data as a part of the source code. Solving this problem seems to be very simple, right? What would be the most intuitive thing to do would be to separate the data files from the code files. And this would allow us to store very large and sort of variable amounts of data, because we just have separate files to store data. Whenever we need the data, we just load it on demand from that. So that way we don't have to worry about the volume of data. We can just load the subset of data that is required from those files. And whenever we need to save data, for example, in our counter example or in our names array example, we would just save the data back to these files. This, on the surface of it, sounds very simple, and is in fact how data-driven applications work. So even though making a data-driven application and using a database sounds so simple, we can't actually do that very easily. For example, if we think that we can just store our data in separate files and split them across multiple files if the files get too large, and then read from the files or save to the files when we need to, just doing these things will soon become an absolute nightmare. Just think about these kinds of things. Just think about these kinds of things that you have to implement. Not only will you have to read from a file, but you'll also have to find that exact subset of data from the file which matches your query. For example, you might want to find all the users in your database who have an age greater than 21, right? And if you try to do that, you'll have to search across all your files and filter by that particular query, which you can imagine is a non-trivial task. Another task that would be quite hard is writing or updating data concurrently on the same file. For example, if multiple people are writing to the file, and say writing to the file is taking a long time, or 3 or 4 people are writing to the file at the same time, then you would have to handle the file writing very carefully to ensure that multiple people don't end up saving inconsistent versions of the file. This problem is even worse if multiple people are trying to update the same data. Imagine a Wikipedia article being updated in parallel by several users, right? How would you know which is the correct version of the article to save and which one is incorrect? And these are just problems when things are going well. What happens when things go wrong? How would you ensure that your data does not become corrupt when your server or your hardware or even your operating system crashes? How will you ensure that you can recover from your data files that you have? How would you secure access to these files to ensure that people who are not authorized to access your database don't access your database? For example, in a large application like Gmail, not all developers of Gmail will be able to access the database of Gmail, which contains all the emails of all the users on Gmail. So how would you secure access to the database? And the worst part is that we would have to solve these problems over and over again for each app that we build, right? These are common problems. And of course, since these have been common problems for a while, database management solutions exist which kind of solve all of these problems for us when we maintain a database. So in a very high performance and in a scalable way, this is what database management systems do for us. They know how to store data in the best way. They even exploit knowledge of the hard disk to ensure that the way that they manage their data on the disk is as efficient and as hard to get corrupted as possible. They provide easy ways and efficient ways of querying the data, of writing and updating the data, and of managing failure and data corruption and recovery methods of how to recover data in case things go wrong. We are almost in a position today where we should never ever implement our own database. We should always use a database management solution, a software that exists, whether open source or proprietary, and use them in our application. So just to make the terminology clear, when we use the word database, a database actually refers to a collection of data. So an Excel sheet, a folder full of files, a CSV, these are all databases, right? But each of these databases are managed differently. For example, Excel sheets and a folder full of files are managed manually, they are not managed by software automatically. And so software that manage these collections of data and manage these databases are called DBMSs, so database management systems. So in web application or in application development, frequently when we use the word database, we actually mean DBMS, but we'll be using them interchangeably. Some common database management systems that you would have heard of are MySQL, Postgres, SQLite, MongoDB. And in fact, databases can be used by your application both on the server side and client side. In these next few modules, we'll be looking at databases that we use on the server side, right? Because that's kind of what we've been discussing so far. We already understood that if we have data in the right data structures in our server-side code, we can sort of achieve what we want, right? So we had articles object, we had an array of names, we had a counter integer. So we were able to get our work done once we had the data structures in our code, right? So what we kind of need to do when we use a database is to essentially get the right data from the database into our data structures. And once they're inside our data structures, we can do what we want. So the hard bit is contacting the database and getting the right data and putting that inside a data structure that we can use easily. And this process is reasonably simple. What we need to do is connect to the database from our application, and whenever required, we query the database and we load the results from that query into our data structure that our code can manipulate. This process is also quite common. This process of connecting to the database, making a query, and loading the results into a data structure in a programming language environment is also a fairly common process. Almost all major web frameworks come with certain type of tool that come with certain packages and libraries to make this easy for us. And there are several tools that exist outside these web frameworks also that make it very easy for us to connect to the database from a programming language environment, make a query and get the results. And these tools or libraries fall into a category of software called ORMs. So before we had a database, and this is kind of what our server-side setup looked like. There was a computer, which is the server machine, and on top of that was our software, which is a web server, right? Once we have the database, our web server should be able to make the request to a database, load data, and then use that to process requests and give out responses. So this is what that setup looks like. There's another software called the DBMS, which is, say, your MySQL or Postgres or MongoDB, and this is your web server. So your web server makes a query to the database processes that query, contacts various files or contacts the disk to obtain the results of that query, and gives that response back to the web server. And then the web server processes that response, loads it into data structures, processes it, and uses that potentially to give a response to the client. This architecture of making a query and response is also the client server architecture, and the database management system is also in fact a server. It's not a web server, but it is also a server. So the web server contacts the database server to make the query and get the response. In fact, because the database management system is a server, it does not actually need to live on the same machine. The DBMS software can be on a different machine, and the web server can contact the database server, which is on a different machine, and get the response. So that is also completely possible. In this quick introduction to databases, these are the key points to take away. A database is a vital component of a modern application, and it should be easy for us to understand how to separate portions of the app that should be a part of the application source code and part of the application and parts of the application that should be maintained as data. We also understood what a database management system is and that a database management system should be used as far as possible instead of trying to handle data operations ourselves, because it can get really hard. We also understood that modern and popular DBMSs solve common problems across the requirement for building an application, and the sort of common problems that they solve are storing high volumes of data, of querying data, of managing concurrent access, of managing access control and security, and managing storage and recovery from failure and corruption kind of use cases.